Hi everybody, welcome to ACM at UC General Body Meeting 13. We zero indexed. If you haven't checked in, go ahead and check in for me at acm@uc.org/c. This is the last meeting that counts for voting requirements. So if this is your second meeting, make sure you sign in because signing in at the elections meeting will not get you voting rights. If you haven't grabbed pizza, grab pizza. If you have grabbed pizza and you want more, feel free to grab it anytime while we are busy doing nominations or during Dom's talk. Yeah, so let's get started. So a couple of reminders. For the first time in a little while, we are recording again. We got the video, and I'm recording on this, and Dom will be recording as well. So that means that afterwards, videos are going to be uploaded to YouTube, but it also means that you are being recorded. Sign in if you haven't, like I said, and then if you have been to 2 meetings and you aren't on our website, the acm@uc.org/members, you should join our website. You can submit a pull request to our GitHub repo, which that's a long URL. All you really need to do is look us up on GitHub or ACM@UC, and make sure you are on our website. It's just a cool thing to do. If you've never used Git, it's a great introductory Git exercise as well. We continue to offer academic services. We're going to do that through until probably the last week of classes. Those are our office hours and our homework help in Slack. Well, homework help in Slack never goes away. But our office hours are Mondays from 6 to 7 and Wednesdays from 1 to 2 in Rhodes 802A. We've got our Slack. I hope everybody here is in Slack, but if you aren't, you should join it. It's a cool place to share news, to share dumb JavaScript modules and make fun of them and things like that. It's a good time. So join Slack at acmcincy.slack.com/signup. You'll be able to create an account there. Follow us on Twitter. I meant to delete this slide because I'm still proud that ACM@UC Nationals retweets us, but this is the 3rd time I've said this. So upcoming meetings, we have one more meeting this semester. So that is Thursday, April 12th at 6 p.m. That's going to be our elections meeting, and that's all we'll do because elections have a tendency to take almost an hour. So we'll be doing elections. If you're running for a position, you'll be able to talk there. I'll talk a little bit more about election proceedings in a second. So let's talk about elections and nominations. We have 5 elected positions. They are our chair, myself, our vice chair right there, our secretary way over that way in San Diego. That's Noah. Our treasurer, Zach, right there, and our webmaster, Isaiah. So those are the 5 elected positions. There is no experience necessary to run. It doesn't matter what year you are unless you're a 5th year. To run or vote, you have to sign in to 2 meetings this year, academic year, which means after today you should have been signed in to 2 meetings. And we will check that for everybody who runs, and then we'll have a system to check that for elections to make sure that everybody who is voting eligible. If you have questions about positions, for instance, maybe you want to know, I'm going to summarize the bylaws on the positions in a second. But if you want, for instance, the exact wording in the bylaws of our positions, or you want questions about what does it actually take to do this position, how much do you have to do, what have you gotten from it, and things like that, reach out via Slack or email, and I'm going to have everybody's Slack name and email in the slides as I talk about them. And so, like I said, elections will be the last meeting of the spring semester. That's required for us. So, requirements, you have to have attended 2 meetings to run. You must be a voting member, which is just attending 2 meetings. All executives have to be in good standing with the university, which just means that you have to have a GPA higher than 2.3. If it's lower than that, you can't be on the exec board. And then no one can hold the position of chair/vice chair for 2 consecutive years, which just means that I cannot be chair or vice chair because this is my 2nd year as chair. So that doesn't impact anybody else. So our election proceedings, it's a trickle-down, a rundown election, which means that we're going to go in this order you see here. That's Robert's Rules of Order, which you notice puts secretary above treasurer. And we go down, so chair, there'll be however many people run for chair. And so, for instance, if it was Bob and Joe running for chair and Bob won, then Joe would have the option to then, even if he wasn't nominated for anything, run for any of the chairs, any of the positions below that. So if you run for chair and you don't get it, but you still really want to be involved, it is perfectly acceptable to trickle down and run for the other positions. And they go in that order. So that means that if you only nominate yourself for webmaster, that's the only thing you'll get to run for. and then voting is in person. We do not do online voting. So I'm going to go down a quick run through of the 5 positions and talk about what their constitutional duties are. And then there is contact information there. So if you're interested in contacting somebody, as always, you can get these slides off our GitHub or write down their Slack or email real quick and shoot them an email or message. So chair, that's me. My jobs are to lead meetings and activities. I really organize our direction and make sure everybody's doing everything they're supposed to be doing. I represent the chapter externally. That means going to ESOC meetings, which are all the engineering student organizations, representing us to SALD, which is the Student Activities Leadership Department, and then in the community and things like that. It has also been a traditional role of the chair to lead Revolution UC, though that's up to the chair how that's handled. And then it's my job to make sure that we're following bylaws and things like that. So the chair is a very open-ended position, but you're the chair, you're in charge. So you get to tell every other position what to do, as you'll see. So vice chair, that's Dom. Your jobs are to preside at meetings in the absence of the chair. So if the chair can't be there, the vice chair steps in. They assist in the duties of the chair. So if there's anything I can't do, I shoot Dom a message about doing it. And then other responsibilities as designated by the chair. Do you have anything you want to add? Cool. So there's hopefully Dom's email and Slack username. So our secretary is Noah. He's over in San Diego right now. The secretary keeps minutes of meetings. They maintain our records, so that's things like our archive and our GitHub and things like that. They are in charge of managing our attendance system. They do a nationals report to ACM. We are chartered by the ACM Nationals group, so we do a report on our finances and our activities at the end of every year, and it is the secretary's job to submit that. They do the logistics of if we wanted to update our bylaws, and then other duties as assigned by chair. And then Noah typically handles social media and email. Our treasurer is Zach. He is in charge of paying bills and maintaining financial records for the chapter. An annual financial report presented at the election meeting. Oh yeah, you have to do that. An annual financial report for ACM Nationals, and then other duties as assigned by chair. Is there anything else you want to add?
You order pizza.
You do order pizza. That is the treasurer's job. Yeah. Yeah, we'll have to talk about that. You are supposed to give a financial report at the last meeting. So it's easy. Yeah, it's very, it's, yeah.
I expect a full balance sheet.
So our last elected position is our webmaster, Isaiah, over there. They are in charge of maintaining the chapter email account, running our website, maintaining our website and things like that. Our listserv and our social media, though we typically share. A lot of these duties end up being shared. They are in charge of our chapter calendar, and then last but not least, other duties as assigned by chair. So the chair gets to tell everybody what to do. Do you have anything you want to add?
No.
Okay.
That's all stuff I definitely do.
So, oh, what?
Why use the word chair?
Because chair is the word in the bylaws. It's the president. It's kind of interchangeable. And okay, I swear I made edits to these that aren't here. There are also 3 committee chairs, which are chosen by the exec board. They are our conferences and education, Andrew back there, our membership, which is Maddie, and then our public outreach, I believe it's called. There might be a public outreach and that's Christian. And so just because you don't make one of our 5 elected positions, there are still other positions which you can indicate your interest to the newly elected exec board in taking up one of those positions and talk about the duties of those. All right, so Dom is going to give a talk on web browsers, APIs, and standard bodies. So a round of applause for Dom, please.
Okay, so this talk is called Browser Internals and Web Standards. I don't have as much time as I originally thought I'd have, so I'll kind of speed through the slides a little bit. But it's meant to be just an overview of web browser internals and web standards. So basically how the processing model of a web page, how a web page is actually processed in a browser, and how new APIs are added to web browsers, who's responsible for specifying them, and how they make their way into the JavaScript language. So here's a quick intro. My name is Dom Farolino, the VP of ACM at UC, as Kurt said. Some of my main interests are in C and C++, browser internals, and web standards, if you could guess. And I'm Dom Farolino if you want to ping me on Slack after this or whatever. And I worked at Mozilla on some browser internal stuff on the graphics team. So here's a really quick summary. We're going to talk about the processing model of the web and how web sites are actually processed in the browser, and then discuss more about web APIs and how they're actually built. We're going to talk about how JavaScript is really just a regular language, how some of these APIs get baked into it and then available to the users and the developers of the browser, and what WebIDL is and how it helps define web standards. And then we're just going to have some questions afterwards. This shouldn't be too long of a presentation, and I'd like to just kind of get more people familiar with this stuff since it's pretty much of an underdog topic as far as like how this stuff comes about, yet the web platform is one of the biggest application sharing platforms in the world, and the developers use the web standards that a few core people know about every day. So how a web page is processed. This is the basic life sort of cycle of how a page goes through the browser. So first we pull bytes down from the network and we process them and we parse them into what we see as some sort of assets, commonly HTML and CSS. So we process this as application codes. And then we construct object models from them so we can actually interact with the object representation of the markup and the styles that you guys write as developers inside the browsers so we can manipulate things and move things around. Once these object models are created, we create something called the render tree, which is basically a big, cool, ordered list of everything that's going to appear on the screen. The render tree, as we'll see in a little bit, is basically derived from the CSS object model and the document object model. Then we undergo a process called layout, where we compute the actual sizes and coordinates of everything on the screen, and we start painting. And we're going to go into these a little bit more in detail. So again, these object models. When you write HTML, this defines the process, or sorry, basically the structure and the content of everything on the web page. This turns into the document object model, or the DOM, that we use internally against an object representation of the HTML markup a developer writes. Similarly, we do the same thing with CSS. We create what's called the CSS OM from it. These are completely independent data structures, which might be a little surprising just because we think of HTML and CSS as converging to create something cool on the screen. But initially in the browser, these object representations are completely independent. And the render tree is basically the combination of the last two. And the render tree, as I mentioned, is going to be part of the DOM and part of the CSS OM combined, and then go through some layout resolution and put some stuff on the screen. This is a really simple process, just sort of walkthrough of how the DOM is constructed. Again, we get bytes, we turn them into characters. We see, oh, this is what content type these characters are. This is an HTML file. So then we build, we lex them and we parse them, and we build tokens and nodes. And from these nodes, we build a tree that is going to look just like this. It's easy to see how this could become a tree because HTML is just innately hierarchical in its nature and just how it works. I mean, everything is written, there's one root HTML element and everything is a child or a sibling or some sort of subset of that. And so it's really easily turned into a tree like this. The head and body in this case are siblings, and we've got some content and metadata under the head, and then all the actual structure that we're going to be able to see ideally on the screen under the body. We basically do the same for the CSS OM. So we create a CSS object model from every style that we get from the developer. And we also have a bunch of default styles that we get not from the developer. So if you are developing a web application and you provide no styles, we still have a CSS OM that we use to work with the document object model internally. And this is from just default user agent style sheets that the CSS specifications define. It's a little less obvious how they could be constructed in a hierarchical way, since CSS isn't innately hierarchical or like written that way, but you can kind of get a picture for how it's happening. So for example, if I gave some styles on the body element that says font is 16 pixels, every single thing that does not define their own font is going to just inherit that. That's why it's called cascading style sheets. Styles cascade down the tree of specificity, and then eventually we kind of merge this and the document object model to create the render tree. It's also called the frame tree in some browsers. Firefox calls it Gecko, which is the rendering engine, and Firefox calls it the frame tree. Most of the browsers call it the render tree. And basically it contains every single visible DOM node that's going to be on the screen. It's important to look at the visible DOM nodes because there's a bunch of DOM nodes like the head and title and metadata and link elements and stuff like that are actually never going to appear on the screen. So we just take, we prune some of this tree and we look at some of the visible nodes on it, and we go through the CSS OM as well. and we find matching styles. So we look at the CSS selectors, and we say, oh, this style here matches this node in the DOM tree, and then we combine them, and we emit a node, and then eventually a tree whose nodes are the render tree, which is, again, every visible node in the correct order that it's going to be laid out on the screen. One thing that we're kind of jumping over here is how we apply the CSS OM styles. We have two trees, the DOM and the CSS OM, but how do we actually combine their styles? This process is called style matching, and every browser does it differently. It's non-standard. Its behavior is not standardized. But basically, it's non-trivial, and it has the potential of being really, really, really slow. If you think of having a massive DOM tree and then a massive CSS OM, and we could have a humongous CSS OM and hardly any DOM nodes, right? Just because if we just get a ton of styles sent down the wire and a little bit of markup, for each node, we're going to have to traverse the entire CSS object model tree to find matching styles and determine what styles match. And then at that point, not just traversing, but how do you determine whether a style matches? You have to look at the selectors and the specificity and actually apply things manually. And different browsers handle this differently. Firefox has, or at least definitely had, a really interesting way of handling this. They broke all the CSS OM nodes into different buckets. Each bucket was a hash table containing different types of selectors. And basically, when we came across the DOM node, we could derive the possible selectors that could be applied to this, given its classes, its attributes, its ID, and its type, and just other metadata that's communicated through the document object model tree. And we start looking through the hash tables for matching selectors. And if we find stuff, then we can apply it. So style matching is something that browsers have been working on a lot to try to make more performant, and actually really, really affects the time to first paint of a website. And again, we are given a yes.
Is that how the new Firefox, whatever they've changed in
I don't think that aspect has changed in a long time. I think that part has stayed the same. Last I knew, that's how they did it, and I don't think they've changed anything like that. They basically have a ton of different hash tables, and then even once they find selectors, it's not trivial to determine how to actually apply the styles and basically what cascades up and what is just inherited and what's kept. But I don't think that was one of the things that's changed with the quantum changes in the latest Firefox, if that makes sense. I don't know exactly how WebKit and Blink do this. Blink is the rendering engine in Chromium, but Firefox is pretty straightforward. It's a pretty good solution to this really difficult problem. So this is what the render tree might look like. If we had, our HTML has one child body, it also has a child head, but we're not even looking at the head in our render tree because nothing in it's going to be visible. Script tags, title, elements, metadata, nothing. And we're going to see we have a body, a header, a main, H2s, H1s, and we're going to get these styles that are applied to them. In this case, we just have a really, really simple amount of styles that are actually applied to each node, like color and font size and things like that. But all the visible data is preserved in this. And the purpose of this is to make sure that we end up painting the elements in order. We want to make sure we have all the visible things, but we also want to make sure that hierarchically we have how things are going to be painted in order. And this just takes us to what I think is kind of an interesting aside. Chromium has something called the fundamental compositor bug. And basically, it's given that markup up there. We have Firefox can render this markup, and Chrome can render this markup. And Chrome renders it wrong. And they're two different things, and they have two different colors that show. And it's basically a layering issue with how like the display list and the render tree end up working in the rasterization stage, and how we paint things and composite to a final layer. There's some small issue in the layout and how we're computing this tree in Chromium, and we end up seeing something like this. This is the smallest example of boiling down this problem. If you want to visit that link, you can to see these for yourself. But in Chrome, again, we have most of the rectangle is blue, and Firefox renders this correctly. Most of it should be gray. Given the CSS specification, Firefox renders this correctly. This is a really tricky bug that I don't know actually much about at all. But I looked it up after hearing some Firefox people talking about how they're bragging that they can render things correctly. And it's the Chromium people, they know about it, right? They have this bug, and they talk about how it's extremely difficult to fix. It's a really, really small thing, and it's like a small fix that breaks a ton of other things and is not impossible, but really, really difficult with the current model of how they align things. And you probably see this very rarely because, if you look, we're using some pretty obscure styles like backface visibility, what the hell. So the next stage is layout. So the render tree consisted of all these DOM nodes with their styles attached to them, but these are still high-level styles that have the form of the values and measurements that are still within the boundaries of the CSS specification. These are not absolute styles, right? Like 10 pixels, or I mean, they could be 10 pixels in the form of CSS, but it's not actual length and pixels and how much of the viewport we're actually taking up. We don't have coordinates and layout calculated yet. So the point of this is to go through the entire tree or the tree while it's being built, resolve the styles according to the CSS box model. And we'll talk about the box model a little bit, but this basically gives us, again, coordinates and sizes of everything. And it's hierarchical, and we can start go from left to right and top to bottom while we're doing this. It's important to kind of touch on the box model, I think. CSS specifications define this box model, and every element on screen basically is a box. There's pretty much no exception. Even if something looks jagged or has a cool side or has a star or something weird, it's represented by a box, and its entire outer frame will be a box. And inside, so we have just the plain old content that is just going to be the size of the content. We can add to this box the overall computed size of this element by adding padding, border, and margin. And this, once they're all calculated and computed, given the previous styles that apply on each node, we're able to, in the layout stage, resolve to get the final styles of some page. So we can see how this looks in the developer tools. You can see this right here. So if I were to select this, and in the style section here, we can go to the computed tab, which if this was smaller, there'd be a tab for computed styles, and see what the actual resolved styles all are on this node here, the one I've selected, this card here. And here we can see how, the content of them and where they're comprised. Okay, so the width of this is 408 pixels, and the padding on the side is going to be 20, and there's no border here, and there is a little bit of margin. Margin actually doesn't contribute to the size of the element. So if you add all these things up, you should get the width of, the resolved width of 448 pixels, which will, since this is responsive, will be changing as I move this site and everything and expand it. And the box model will stay consistently updated. And so that's roughly how we represent things on the screen. And then final stage is the painting stage. The painting stage basically consists of two parts. We rasterize and then we composite. The rasterization stage is where we basically draw pixels. It's known as the expensive stage in painting and rendering in browsers and a lot of just different graphical applications, things like CAD programs and stuff like that. Basically, we draw pixels into a huge buffer, and these pixels are the pixels represented by the box model of some elements. Every element in the render tree knows how to draw itself and all of its children, and so we can mark certain things as dirty, certain things as clean, and re-render portions of the page as we see fit. It's expensive because we're literally writing all the pixels that we need to represent to the screen to some sort of buffer that is going to be composited in a layer. Solid colors, for example, are really cheap to paint. We just sort of spit them all out, and it's sort of like a linear write to a big buffer. And some more complicated things are tougher. We have to do a lot more math for gradients or pictures or certain more composited CSS effects and blurs, for example, and things like that. So this can be expensive depending on the size of things that are actually rendered. The compositing stage is the very final stage before the user actually sees something on the screen. It's pretty simple. We just take everything that we've rasterized, collapse it to a single layer, hope that the ordering is correct in the case of Firefox, and then we ship it off to the user. And that's basically it. A lot of this is probably done on the GPU when possible, and definitely not blocking on the main thread. Any questions on that aspect of this? Just the general portion of how a browser is processing websites? Okay, so the next thing, we covered HTML and we covered CSS, but we haven't really looked at JavaScript at all. Or web APIs and how they exist and why we can make websites interactive, etc. So, APIs on the web for developers to use, they're exposed via JavaScript. They just exist as global functions, properties, or constructor functions on the global object. For example, we have some like commutation observer, DOM exception, set timeout, and the fetch method, and things like that. There's also some other properties that are not functions in this case. But we have to understand exactly what JavaScript is, because JavaScript doesn't contain any of those functions in itself. It's really just a regular programming language that can be run on any computer. The history of it's actually kind of interesting. In the mid-90s, Netscape tasked Brendan Eich with creating the JavaScript programming language. They wanted him to create a Java-like programming language to work on the web. And he made a really cheap copy of that, basically, in 10 days called JavaScript. He determined that anything too Java-like was going to be too complex and didn't really fit for the model of the web. And so he wanted something else that was more of like a basic, easier scripting language, so he created JavaScript. The point of which is to have a programming language on the web that we can modify, that we can use to manipulate the DOM and the CSS on. These things exist in the browser, but they were never exposed to the developer before. So by giving the developer access to them in a secure way, of course, through JavaScript, we can actually modify the page and listen to events and do all kinds of really cool stuff with this model of thinking. At this point, one implementation existed, and it was the one in Netscape. And then Microsoft stole it, and they took the entire thing, bugs and all, and put it in Internet Explorer, and they ripped it off, and they started winning with it. And IE was really taking off. Netscape basically died, and before it died, they wanted to standardize it because they knew they had multiple implementations of the same language. So if there were going to be multiple browsers, Brendan Eich later on went to create Mozilla Firefox. If there were going to be multiple versions of the same language, they better standardize it. So they standardized it through ECMA. But before I get to ECMA, here's just a list of some of the current ECMAScript engines. So they did, if you give any sort of implementation or some sort of practical implementation of something to a standards body, they're going to make it as general as possible. So they went off to standardize JavaScript, but they didn't standardize JavaScript. They turned it into ECMAScript because the organization was called ECMA. ECMAScript was a scripting language specification, and it works for all kinds of different languages, JavaScript being one of them. And there's a bunch of different implementations of it. A lot of them ended up being used in web browsers. V8 is Google Chrome's and Node.js's rendering engine. Chakra is the one used in Microsoft Edge, and JScript was the one that they stole from Netscape. So what is ECMA, basically? Well, first I'll show you the specification. Yeah.
So all of those JavaScript implementations all fit the same standard.
Yes.
So the behavior of them should hypothetically be consistent, but I assume there's just performance differences?
It's not even so much as performance differences. Basically, they all implement the same spec, but it's really where they're used. So I think one of them up there is I don't know, used for like Adobe Flash or something. I don't know. And it is basically JavaScript. You could easily plug it into a browser and mess with some bindings, and it would end up working. It wouldn't break anything. I mean, it would need like some extra care just because like it's not an exact plug and play, but the language is going to be the same. ECMAScript is what runs in the browser, not JavaScript. JavaScript happens to run in the browser, but it's not the only thing that can. So yes, there are probably a lot of performance differences just because like certain working groups are more dedicated to making sure the implementation of a language is really, really good. Like Chrome's V8 team is like I don't know, 100 or so people, and like Firefox's JavaScript engine team called SpiderMonkey has about 6 people on it. So the performance differences will be a little bit different, but they all ended up implementing the same specification. And the spec can be found, it's managed by the Technical Committee 39 of the ECMA group, and that is supposed to be here. Okay. This is what the spec looks like. Basically, it's all cramped on this terrible resolution now. Why they went with this logo, I don't know. It looks terrible. And oh, it's not what we wanted. Yeah, so basically, this is the specification. All kinds of types and everything are defined in here, and it's literally just a language specification, super high level. There's actually some history included in here as well. Seems to not be loading everything correctly, but that's basically it. So again, what is ECMA? It's the European Computer Manufacturers Association. I really do not know why they went through this committee or this organization to standardize it, because it seems kind of obscure, but I guess they did. But that would also explain so many Oxford spellings that take place in the specification, like behavior and analyze and things like that. It kind of drives me crazy when I read it, but it's also kind of funny. So I guarantee you've used the Web API, because honestly, everyone has, really. Even if you don't know it, if you've visited any major site, you basically have used the Web API. These are things like fetch, document.query selector, XML HTTP request, which is old and nasty. These things are visible through JavaScript in the browser, but JavaScript doesn't actually contain this. I mean, Node, for example, is the effort to run the JavaScript engines not in the browser, but on the desktop or on servers or anything like that. And if you type in any of these things, you're just going to get some sort of error or undefined if you don't invoke them, because they don't exist in the language at all. But they are baked in to the browsers. So you're probably wondering, like, how on earth do we actually get these things and where do they come from? And the answer is web standards create these things. So here are the two probably major standards bodies. On the left, you see the W3C logo, the World Wide Web Consortium. And on the right is WHATWG, or the Web Hypertext Application Technology Working Group. And basically, the W3C for a long time was responsible for authoring the HTML specification and determining exactly how certain primitives in the browser work and how web pages should be rendered and stuff like that. And they also maintain all the CSS working group drafts to specify the CSS style language. In 2004, after a W3C workshop, a couple members from Mozilla and Opera Software broke off because they were concerned with the direction that W3C was taking the HTML spec in, and they basically broke off and formed their own standards organization and recreated the HTML spec because W3C was focusing a lot more on XHTML and XML as opposed to HTML. So the WHATWG kind of stepped in, created their own standard, and all the implementations at the time. Did someone ask something? Oh, thought I heard. Okay. All the implementations at the time kind of went along with the WHATWG's representation of the standard because it was known as, at that point, more of the authoritative source for HTML. Other standards that the W3C maintained are still respected and were at that time. But basically, the WHATWG runs HTML and a lot of other standards now. A standards body is basically responsible for defining and maintaining web standards, in this case, web standards bodies. And they work closely with vendors and browser implementers to ensure that there are actual conformant implementations. We want the spec to just be a little bit ahead of all the browsers, and the browsers to want to have a motivation in implementing the specification. So they're constantly working with the developers and the browser engineers to make sure that pages work the same on each independent implementation of all the different web standards. So what is a web standard? Or I guess really just a standard in general. It's pure theory. It just describes the attributes of something, sort of the observable and behavior of certain objects that we define in the standard. But it's nothing without an implementation. It needs implemented because it's purely theory. So here's a decent example. Sticker.how. Someone I do a little standards work with created this as their first little try at it. And it's a laptop stickers specification. And so basically, it's really crucial stuff. There's the square sticker, and then there's the hexagon sticker. And the hexagon sticker, apparently, as a definition, must be represented by a rectangular hexagon where the largest diagonal should measure 5 centimeters and blah, 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 this and that. This is not a laptop sticker. I can't put this, I could, but I can't put this on my laptop, but somebody who implements the standard or creates the sticker can. And then I can have a laptop that conforms to this standard. And this standard defines roughly what a sticker consists of and how they work with other stickers to make sure that they all fit on my laptop nice and pretty. So it's literally just pure theory, but it's nothing really without its implementations and its backing. So how are web standards written? Well, they use a couple tools, and they're really simple. The first is BikeShed. It's written by Tab Atkins Bittner Jr., who works at Google and is the lead editor of a lot of the CSS working group standards that are produced by the W3C. So he basically writes CSS in the standards, and the other browsers implement it. He wrote what's called BikeShed, which is a spec preprocessor, and allows us to do really fancy things in our specs, like cross-linking between different web standards, and definitions and headers, and really, really pretty stuff that we don't really have to work hard at. We just kind of give it text content and link to other things, and it's responsible for building the document out of not much stuff at all. It's really, really a good tool. And the second is, okay, actually, yeah, so we use this to write the general text of web standards. For example, this is the request, some of the textual standardization of the request class in JavaScript. So this is accessible through JavaScript, just request as a constructor. Internally, a request is going to have all these different flags that they kind of give it, and BikeShed helps us, kind of makes us look nice and cross-link to other important things. We also use something called WebIDL. This is kind of interesting. It stands for Web Interface Definition Language, and it looks like this. This is how we write basically what the web standard, what some sort of web API's interface is going to look like. this is roughly going to correspond to its exposed JavaScript object because it's kind of what it's explaining. This isn't JavaScript, it's not C++, it's kind of a mix in between, and it will eventually help us bridge the gap between JavaScript and C++ when the implementers are working at it. So we just find things like read-only attributes and types of data and things like that. So again, what is IDL? It stands for Interface Definition Language, and it is used to create a communication between two entities. This is IDL in general. So think of like remote procedure calls in like old like computers or something like that. We've got you know, a server and a client or some sort of multiple languages, and we want two ways to communicate. So instead of writing a bunch of classes and network communication stuff here and writing a bunch of classes and network communication stuff here on the server, one's on the client, one's on the server, we can instead define some IDL, which we write in the middle, which is just a little bit of text saying, oh yeah, I want another channel of communication between these two people. And we tell it that we want this second channel of communication, and we write an IDL parser to go in and spit out the right C++ code to actually make that work. Because a lot of it's going to be boilerplate with like the communication between two entities. So it's, language bindings are good for this kind of stuff in client-server communication. So how about WebIDL? Well, it's also an interface definition language. But a better question is to ask what its responsibilities are. And so let's look at this. So if you're a JavaScript user, you're dealing with things in terms of JavaScript types and paradigms, right? There's a few JavaScript types like symbol and number and object, and you're dealing with properties and the way that JavaScript exposes them. If you're dealing with an implementation and you're writing a browser, you're doing C++ or Rust these days, basically, for browsers. That's mostly what all the rendering engines are written in. And you're dealing with those kind of types. So WebIDL defines these really abstract types that are just sort of abstract away some of the complexity from the ECMAScript standard. And it standardizes the conversions between these ECMAScript types and these abstract types. And then in a proper WebIDL conformant parser will parse WebIDL and create bindings between JavaScript and C++ so that you can actually use those values. So when you get to C++ land, you know you're dealing with the right stuff that was passed in via JavaScript. So it defines things, some of the abstract types that we'll talk about in a little bit. But a language type versus a specification type is basically what it comes down to with this IDL stuff. A language type, again, is just stuff that's exposed to the users of a language. C++, we've got ints and chars, and JavaScript, we've got symbols and objects. So it's the primitives. The specification types are just what a spec uses to describe abstract functionality. It does not bury down into the implementation specific stuff. The implementation is tasked with conforming to the abstractness of the standard. And it's really helpful when we deal with multiple implementations, because if we have a standard, we might want to say we have this abstract list of things. We don't want to say we have a C++ vector of stuff. No, because if I write it in Rust, I don't have a C++ vector. So we do really abstract operations and structures so that other things can implement them. For example, there's the DOM string abstract type in WebIDL. And at the top, we see part of the console interface. And it has a time method that takes in an optional DOM string label, which is basically a type in WebIDL. And the type in WebIDL has this algorithm to resolve its ECMAScript value. And it basically defers to the ECMAScript standards toString algorithm here, which actually just gets the value. This is a really, really simple conversion, but some are really complex, and they resolve to a value in a much different and less clear way. So the point is, the IDL parser reads this IDL and says, oh, we want to make sure whatever we're given in JavaScript gets converted to a DOM string. A DOM string has this certain conformance here, and that way when we're in C++, we can accept a DOM string into something, and we know exactly what we're getting, because we don't have to redo the language binding conversions every time manually ourselves, because we've defined this abstract type that can do it all basically for us. And so there's all kinds of different types when you're dealing with standards and implementations and stuff like this. So for example, the ECMAScript standard has two different types of types. Specification types, which are just abstract ways it defines collections, like a list and like a record and stuff like that. Then there's the language types, symbols, objects, things that you use as a JavaScript developer. Then there's the C++ types on the far left, and we'll get to the WebIDL in a bit, which is just int, bool, and string. And eventually, if we want to make a language or an implementation of the ECMAScript specification in C++, we would probably do it in something like C++, just because that's like the most common implementation for it right now. we would write our bindings manually. And then whenever we'd want to talk with web standards, we'd want to make sure that we're not doing these bindings over and over again ourselves. So we introduced the WebIDL type, which is just an abstract version of the ECMAScript types. And it does all kinds of fancy algorithms and conversions for us that we mentioned. And as long as our C++ binding can implement the WebIDL specification, which defines things like DOM string and any and dictionaries, then we know we're getting the correct bindings every time. So we have to basically just write an efficient and correct WebIDL parser, which is not terribly difficult to do. Each implementation has one, so that they can maintain correctness between web standards and make sure that the bindings are correct. That's basically it for the talk. So it's kind of an interesting thing, web standards. I feel like, again, not many people know about it, and it probably bores a ton of people, but that's okay. It interests me. So if you want to get involved, you should join WebWug on IRC or open an issue on one of the specifications if you are interested in working on something or modifying something. The process is pretty simple. I mean, any sort of observable platform affecting changes requires 2 implementers to be on board. One of the major, the list of major implementers that the WebWug recognizes are basically Chrome, Firefox, Safari, and Microsoft Edge. You make some corresponding web platform tests. There's a big repository of all kinds of tests whose purpose are to test any implementation of these standards to make sure that they're all conforming. And then you file some bugs with browsers, merge something into the spec, and if you want any more information, you can see either of the 2 posted links to take a look at some more stuff if you want to get involved. That's all I got.